everyone. Thanks for coming out in whatever time zone you're in. Let's see if I can get, okay. Let's see here. Get some screen sharing going. Okay. There we go. All right, can everyone see my screen? I can't see you right now, so someone's gonna have to unmute and tell me they can see. Okay, great.
Yeah.
All right, I'm gonna talk about the late, great Arecibo Observatory. If you have questions while I'm talking, feel free to unmute yourself and ask, or you can type them in the chat and I'll get to them when I'm no longer full screen. So I graduated with my master's in 2011, which is not usually something you do in course 12 planetary. You usually don't get a master's, and I was trying to figure out what to do with myself, and I had been talking with the head of the Planetary Radar program at Arecibo Observatory at a conference earlier in spring 2011, and he said, the money's coming, and we're going to have money to hire more people. And I said, yeah. So I went and I did some other things for a few years and ran into him at a conference the next summer, and he said, the money's coming. And I said, you told me this a year ago. And finally, I emailed him a couple months later, and he said, the money showed up. We wrote a job description with you in mind. Please send us a resume and a cover letter. And within a month or so, I had moved to Puerto Rico. I'd never been there before. And so this is a little bit about the science, the legacy, and my personal experiences working at Arecibo. I am an asteroid radar person. My email address is asteroid@alum.mit.edu. So the focus of this talk is going to be asteroid science. I might mention some of the astronomy that happens there, as well as the aeronomy and atmospheric science, but really it's an asteroid talk. So I'm going to talk about how we study them from Arecibo, what they look like, and why we study them. So for a lot of us who weren't course 12 majors, when we think of asteroids, we think of The Empire Strikes Back in 1980 with the Millennium Falcon navigating an asteroid field and C-3PO going on about the rather low odds of surviving. And so while this is a nice, science or fantasy version of asteroids, let's actually talk about what asteroids are and where they came from. Asteroids come from about 4.6 billion years ago when they formed as the solar system formed. They were the little planet that couldn't, as gas and dust condensed into boulders and planetesimals. Some of it formed into planets. Some of it never quite accreted to be large enough to form a planet. And some of this material, once it formed into a planetesimal, was broken apart by impacts. And so that material then falls to Earth sometimes. And so we know that these asteroids are 4.6 billion years old because we get rocks like this one falling to Earth, and they have those white specks in it are called CAIs. They're calcium aluminum inclusions, and they're super refractory. They're the first solids to condense out of the solar nebula. And so this meteorite itself is a couple centimeters across. And it's super cool that you can have something in your pocket that's older than the Earth, that has pieces older than the Earth. So meteorites are one way of studying asteroids. They provide samples of the conditions in our early solar system and extraterrestrial bodies in general. One of the cool things about this meteorite is it fell in Mexico in the late 1960s, just as the Apollo program was ramping up, and all of these laboratories were getting ready to study extraterrestrial rocks. And so it was very fortuitous that the Apollo program was coming online as this meteorite fell to Earth. So there was all these labs geared towards studying material like this. And actually meteorites like this are about 10 to 15% hydrated minerals. So they're about 10 to 15% water. So the impacts that send these asteroids to Earth, maybe some of you have played asteroids once or twice in your life that have shot these things apart. So we kind of think about asteroids being this cosmic shooting gallery bent on coming to destroy Earth. So the asteroids don't actually hang out around little spaceships that shoot little pellets at them to blow them up. They hang out in orbits generally between Mars and Jupiter. There are about 1 million asteroids over 100 meters and at least 20,000 near-Earth asteroids that pass close to Earth or within the orbit of Earth plus some, about 30%. So we think about these million or so asteroids, and we see these images of them orbiting the sun, and we think, gosh, this has got to be really dense. So this is a plot of the motion of objects in the inner solar system over a 2-year period. The green dots are main belt asteroids orbiting the sun, and the outer orbit is the orbit of Jupiter. You can maybe, if your screen's really good, see a little blue circle going around in the positive theta direction. I love that I'm talking to MIT nerds, so I can like go all mathy on you. And so that's Jupiter orbiting with all these green asteroids, which are main belt asteroids, and the red asteroids are near-Earth asteroids. So this image is about a decade old, and we've discovered a lot more asteroids than when this GIF was made. But we look at this and we think, gosh, these asteroids have got to be really dense. And in fact, the density of asteroids is not very dense. On average, there's a separation of 2 million miles between asteroids, or about 8 times the distance from the Earth to the moon. If you scale the average size asteroid down to the size of a potato, then the potatoes would be about 1 kilometer or half mile apart on average. So there's a lot of empty space between asteroids. So we've had Han Solo telling C-3PO, never tell me the odds, and C-3PO is going on about how there's a likelihood of surviving an asteroid field of 3,720 to 1, when it is actually the case, at least in our solar system, that every spacecraft we have sent through the asteroid belt has survived the asteroid belt. So in our solar system, the odds of successfully navigating the asteroid belt is 1 to 1. All right, so sometimes asteroids come a little bit too close to Earth. This is Barringer Meteor Crater in northern Arizona. It's about 1 mile wide and almost 600 feet deep. It formed in about 10 seconds. So it was a really bad day to be in northern Arizona when this hit. Most meteor craters on Earth are filled with water, or they're got plants growing on them, or have otherwise eroded away. So we do see meteor craters like this, and this is actually where Apollo astronauts went to go study impact craters and practice for going to the moon. Another time we've had sort of a recent close encounter with an asteroid was about 8 years ago in Chelyabinsk, Russia. And we learned a startling fact. Every Russian has a dash cam in their vehicle. And they all stay pretty chill when there's this big explosion happening in the early morning sky. And there's actually pieces of Chelyabinsk that were collected. I've got one in another room, and you can't really see it very well over the webcam. But if you want to see pieces of Chelyabinsk, I encourage you to go search for it. We also learned that everyone will go to the window when there's a big explosion in the sky and then have the shockwave and broken glass hit them. So it's really important to study asteroids for hazard mitigation in the unlikely event one will hit Earth anytime soon. But in the event that one may come hit Earth, it's really important to figure out what an asteroid's made of, how big is it, how dense it is, what's its orbit like, because all of that information is scientifically interesting, but all of that information is also relevant if you're trying to do any sort of impact mitigation with Earth. Are you going to try to change its orbit through an impactor on it, or painting half of it white and letting the Yarkovsky effect change its orbit? There's a lot of things you can do if you have enough warning. And then finally, another reason to study asteroids is space resources. Water is really important if you want a sustained human or really robotic presence in space. You can use that water for drinking, for shielding, for splitting into rocket fuel. And with some of these asteroids that are about 15% hydrated minerals, that's a really good source of water. So there's 1 million asteroids at least, probably 2 million, depending on what size you think an asteroid is. And we've sent spacecraft by some asteroids, and we see these asteroids as resolved worlds from these spacecraft. But each of these images costs hundreds of millions of dollars to get. You can't do this when you want to start studying the population of asteroids. But it gives us these really cool close-ups of these asteroids. We see that they are a variety of sizes. There are a variety of shapes. Some are really pockmarked, some are a little rounder. We also see some comets in here, and there's this huge range of asteroid sizes that we've looked at before, from spacecraft dating to, I think, Galileo in 1993 was the first spacecraft to visit an asteroid. And it even has a moon, sorry? It even has a moon called Dactyl, which is kind of cool. So if you study, so each of these images costs about hundreds of millions, $1 billion to get a mission in space to get this image. And so that's not sustainable for looking at a population. So to discover asteroids and study them from the ground, we use ground-based telescopes, which are great. You can actually see about 2 or 3 little asteroids moving through this field. There's about several images that were taken spaced apart, and this is how asteroids are discovered. This is how we know that there are millions of asteroids. And this is a great way to characterize asteroids, but it has some drawbacks, the least of which is weather. This is winter in Tucson, and winter in Tucson means we have spectacular sunsets, but when you have clouds in the sky, you can't observe with your ground-based telescope. So that's a bit of a drawback. And so clouds make it really hard to observe at night. So there's a way to sort of bridge the gap between asteroids as points of light and the information that gives us over a very long time baseline, and asteroids as these really high-res spacecraft targets, and that's radar. Radar bridges the gap between optical telescopes and expensive space missions. And there were 2 planetary radar systems. As of a little over a month and a half ago, there is 1 planetary radar system. So the focus of this talk is Arecibo, which was a 305-meter diameter dish with a 1 megawatt transmitter at 2.4 gigahertz. It's a fixed dish. It could point 20 degrees from zenith in either direction. It's another system that was used for planetary radar and asteroid studies was the Goldstone Deep Space Network dish. So it's a little smaller. It's about 18 times smaller at 70 meters. It has a 0.5 megawatt transmitter. It transmits at a higher frequency, and the dish is fully steerable. So it can track objects for longer, but it can't see as deep. So Arecibo is super unique because it was this for a variety of reasons. One, it's 305 meters across. Up until a couple years ago, it was the largest single dish radio telescope on the planet. It's a multi-use facility. It wasn't just used for asteroids, but also radio astronomy, galaxies, gas, pulsars, and ionosphere and climate studies. So here's the dish itself. Some friends came to visit in my last year working at Arecibo, and the platform, there had been an earthquake and we were worried about damage to the platform, but one of them had a pilot's license. So we went into town, rented a plane at the airport, and flew around the observatory, which, going on the platform is pretty cool, but flying over it we'll have to do. So you can see it's pretty big. You can see it's in this mountainous karst interior of Puerto Rico, all these big sinkholes, which is really convenient. If you want to build a 305-meter dish, just find a 305-meter sinkhole. Here's a construction photo that I think is really interesting. This is from 1960. It took 3 years for construction to finish. They started construction in early 1960, and so this is February 63, and then by November 1963, the observatory was open and getting data. So you can see that they had this platform. They built the towers first, suspended the platform in the air, and then built the catwalk going out to it. And as they were doing that, they were carving out the last little bits of the sinkhole and installing the dish. And the reason they selected Puerto Rico was there were a couple of reasons. One, it was US soil. Puerto Rico is a US territory. So if the original, I think, owner of the facility, I believe, was military, and so they wanted this facility to be on US soil. They wanted a latitude that was not too close to the equator for studying this ionosphere phenomenon. and they wanted a location away from radio signal interference. They wanted a radio quiet area. So the sinkhole that had a tobacco farm at the bottom was a place that met all of that criteria. Turns out the ionosphere scientists, the astronomers that designed this facility, made an order of magnitude mistake. And for the phenomenon that they were trying to study, 100 meters would have been fine, or 100 feet would have been fine. So building a 1,000-foot dish was a great mistake because it means that other people could use it. So a lot of people my age think of Arecibo. When we think of Arecibo, we think of GoldenEye. We think of James Bond. We think of the N64 game. We think of these towers coming out of the hills. We think of this dish coming out of the water. And that's kind of true because the humidity is so high in Arecibo that the dish was effectively underwater for its 57-year career. The other thing to note here as well, that's an actual, I believe some of these shots were actually at the observatory, but you can see a couple of things. You can see this azimuth arm with a big line feed antenna hanging from it. You can see the triangular platform, and you can see the circular track that the azimuth arm rotates around in GoldenEye. The other movie that we think about when we think about Arecibo is Contact. This was filmed a couple years later after a big upgrade to the telescope, including this Gregorian dome, which allowed them to focus radio waves instead of to align to that line feed antenna. Allows you to focus waves to a point and allows you to focus waves to a point and then swap instruments more easily for radio astronomy. So this is a space shuttle image of Puerto Rico. Puerto Rico is about 100 miles across by 70 miles wide, and you can't really see, here we go. Ooh, can I annotate? Mouse. Great. I believe Arecibo is about here on sort of the northwest center of the island. Or sorry, nope, I can't get a cursor. That's fine. Puerto Rico is in the northwest sort of central part of the island, away from the San Juan metropolitan area. So here are some images of the dish that I've taken while I was there. Are there any ham radio nerds in the house? This is the 430 megahertz waveguide for the 430 megahertz atmospheric radar. And I had a friend from MIT who came to visit, and she'd worked at the South Pole Telescope, which is a much higher frequency telescope. And she takes one look at this line feed and says, at this waveguide, she says, this isn't a waveguide, that's like an air conditioning duct, because she was used to waveguides that were much smaller. So for scale, you can see in the upper left of this photo, a couple of folks on the platform, so you can get just an idea of how big this thing is. One of the cool things about the platform was that it was really stable. You could go up there and it felt like you were on solid ground, which makes sense because you've got this big telescope doing precise astronomical observations. You don't want it moving more than a couple of centimeters. This is a photo from the bottom of the dish looking straight up. I always liked this photo because this is a perspective a lot of people don't get on the telescope. You can see really clearly the Gregorian dome that moves along the azimuth arm. You can see the circular track, the triangular platform, and all the cables holding the platform up. Here's another photo from under the dish of some summer students. And you can see a couple things here. The dish is transparent to sunlight, and that's because you want plants to grow under the dish so that you don't get erosion. And so those panels were all made from perforated aluminum. To give you a sense of scale of the observatory, this was a rendering done by one of the postdocs who was really into Blender. And this shows you that the telescope would routinely look at asteroids smaller than the dish itself. This is something that most telescopes cannot claim. They do not often look at objects smaller than the telescope. So this is a 250-foot asteroid chilling in the 1,000-foot dish. Okay, so radar basics. How does planetary radar work? Well, you transmit a radio signal at a known frequency for a certain time interval, and the radio waves bounce off the target and eventually return to the telescope. And in order for this to work at Arecibo, for asteroids, to study asteroids, you need a lot of power, which we'll talk about in just a second, a big dish, which we've already discussed, and a close target. And so asteroids come within a few lunar distances from Earth, and so they satisfy that final criteria. Okay, so the power grid in Puerto Rico, as we have become very familiar with in the last couple of years since the hurricane, is not terribly stable. Every afternoon in the rainy season, the power would go out, the backup generators would kick in, and life would go on at the observatory. This was just perfectly normal. In order for the planetary radar system to run, there were 4 diesel generators, each of a ½ megawatt. And so you get 2 megawatts from these diesel generators. And so if you are a high voltage nerd, this is a series of the power supplies that get you up to 65,000 volts at 33 amps and 2 million watts. So it's a very simple circuit, except what comes out of it is 2 million watts. Please don't try this at home, especially with 33 amps. So where do all these watts go? So the watts go into these things called Klystrons, which create radio waves through high voltage and magnetic fields. These things run hot, so they're cooled with about 300 gallons of water per minute. And if you look on the right of this image, you can see something, the tube that's going to this Klystron says Brewmaster, and that comes from a homebrew catalog. It's not like you can go down to the hardware store and say, I would like 1 Klystron, please, and the associated cooling system. Pretty much everything at Arecibo is a one-off and has to be built from whatever you can find. This is the interface, the UI for the radar transmitter. This is an old MS-DOS machine, and this was a really rough day for observing. A lot of things had gone wrong. Red means there's a fault, so the high voltage power supply was having some issues, the 480 volts AC was having some issues, and the crowbar was having some issues. So if you're not familiar with high voltage, in the bad old days, if your power supply was going to get overloaded, you'd drop a crowbar over the 2 terminals to short it. And so now there's an automated crowbar circuit that drops the equivalent of a crowbar over the terminals of the power supply. This is the transmitter and the receiver. So the receiver is on the left. It's got that orange film covering the horn that you can see. Each of these is about 12.6 centimeters across. You have the world's most sensitive planetary radar receiver on the left, next to the world's most powerful planetary radar transmitter on the right. So you cover the receiver when you're transmitting, and you uncover the receiver when you're not transmitting, otherwise you will fry it. And that is not the goal. Here are some of the other, this is the radar receiver, the transmitter also is in this room. So all of these instruments in the instrument room are on this lazy Susan table that rotates. So when you're doing planetary radar, the receiver rotates in. When you're transmitting, you rotate to the transmitter. If you're doing using an instrument that's used for studying pulsars, you can swap that in. So the whole point of this Gregorian dome was making it easier to swap from instrument to instrument and not having to build a big line feed antenna for each wavelength. The instruments themselves are cooled with liquid helium. So here are some of the helium compressors. And then this is a photo from the platform looking down at the dome, and you can see some of the big fans that get 1 megawatt of waste heat off of the transmitters. This was sunrise early one morning. I think it was the only time that I had some friends visiting. It was the only time on the schedule that there wasn't something sensitive going on, so we could go up and take photos and not worry about the radio frequency interference from our camera shutters interrupting observations. This is the control room at Arecibo. Some of you who've seen Contact will recognize this tile floor. This is the atmospheric radar console, and it's got a bunch of knobs and dials, and it looks very old school because, you know, the things still work from when it was originally designed. This is the planetary radar system, and so there's a lot of cabling that happens. if you design a backend for the radar that doesn't involve any cables, that's great, but then you have less flexibility when, say, a spacecraft's radar transmitter has broken and the spacecraft people want you to transmit at their spacecraft using something that we don't usually use all the time. So having these complicated systems of filters and amplifiers gives you the freedom and the flexibility to really deal with whatever scientific problem you come across. Also, because the telescope is a giant voltmeter, the signal isn't officially measured until after you've done all the signal processing to it, until it's finally converted into a power when it goes into the computer. So any of this processing, you're not losing resolution as you downshift the signal and eventually get it to a place where you can do analysis. Because radar is not affected by clouds, day, night, lightning, you can observe at all hours. And this sometimes leads to some late night control room naps. This was my office mate who was running the radar group for a while. I don't know if he knows that I have this image in these shows, in the show. So radar is great. You create your own radio waves. You know when you transmit and when you receive. You use the speed of light and time to measure distances and speeds, so you can do things super precisely. The sampling time at Arecibo is about 50 nanoseconds, so you can get some really high precision measurements of asteroid positions and velocities. You can transmit and receive pretty much in all sorts of weather, and the 2.4 gigahertz frequency means it's not as affected by water in the atmosphere as higher frequencies are. And you get these higher resolution details of asteroids and comets with just a few minutes of observation compared to images that might take days or years if you were using a ground-based optical telescope. And you get super great orbit measurements. Okay, we're gonna go a little nerdy on the signal processing. There's two types of radar that Arecibo does. One is a continuous wave. So you transmit a continuous wave in one polarization frequency at 2.4 gigahertz at an asteroid. That signal reflects off the asteroid and you get a whole bunch of Doppler shifted waves at a variety of frequencies coming back. And so you do a whole bunch of Fourier transforms on the echo and you get a spectrum of the asteroid. So the spectrum looks something like this of an asteroid. You have a nice sort of curve, and this asteroid has two spikes, and the two spikes actually correspond to two moons that this asteroid has, which I think is super cool. Because the moons orbit the asteroid more slowly than the asteroid rotates, the signal from the moon sort of bunches up and gets stacked into those nice spikes. So Arecibo is really great at detecting things that move slowly. The slower things move, the more signal you get back. The other thing you can do with Arecibo is if you have an object that's close enough or large enough or rotating slow enough that you get a high signal to noise, you can get these delayed Doppler radar images where you have Doppler shift on the x-axis and range or delay on the y-axis. So you're effectively taking a three-dimensional rotating object and projecting it into cross-section versus velocity. This means that if you have an object that's perfectly circular and rotating with the pole perpendicular to you, you don't know if the part of the asteroid that you're getting back is in the north or the south of the asteroid. So you have a north-south ambiguity. So you can break that ambiguity with ground-based optical observations or waiting a couple of days until the asteroid's at a different angle. So it's pretty much like taking a potato, cutting it up into little pieces and trying to figure out what the original potato looked like. But with a lot of forward modeling, you can get shape modeling, and it's a terrible, terrible process. If anyone wants my rant, I'll save it for the end. Forward modeling is hard, especially when it's CPU limited, not GPU limited. All right, so the observed asteroid population, let's do some science. radar is this relatively inexpensive method of studying the population of near-Earth asteroids when you want shapes and getting fine resolutions of about 10 meters on these asteroids. We can get 7.5 meter resolution on these objects. You can't do that with a ground-based telescope. Knowing the shapes of these asteroids is super important, if only to understand the population of asteroids, and is also helpful for space mission planning like OSIRIS-REx, which went to this asteroid called Bennu, and part of the reason Bennu was selected was because we had a shape model of it. We see a whole variety of shapes and sizes of asteroids, and I'll go over some of these radar delay Doppler images that we have of objects as seen from Arecibo.
Sandy, we are just a little past time, so I don't know if we can, if you could stick around after to answer some of the questions that's in the chat.
Yeah, I'd be happy to answer them. I didn't realize it was a half hour. I'm so sorry. Okay, these are 3 asteroids. They're about 400 meters across. I will stick around and answer questions in the chat.
Thank you so much. This was really awesome. Love the images of the asteroids and the observatory. Thank you, Sandy.
Thank you all.